Hello people, so we are in chapter 6, chapter 4, section 6, coordinates and change of basis. We are going to start with an analogy, so you understand exactly what's going on. It's very simple if you understand what's going on. So we have here our dear puppy, dog, and the idea of the entire section is to have different words that represent the same dog in different languages. So the idea is to find the coordinates or the words in different languages for the dog. So language will be our basis. You know that every linear space has a basis, actually has infinitely many of them. So as soon as we change basis, coordinates of people living in the linear space change. So here our puppy is one guy living in our linear space, and the basis will be a language. So we change the language, we change the basis. The coordinates or the words will change depending on the language. So that's the idea of the intersection. It's very simple to understand. Now what we would like to do is to build kind of dictionary if we want to go from English to Spanish, to translate as many words as possible, not just one. Then we will need a dictionary. Well, dictionary in linear algebra will be our transition matrix from English to Spanish. So basically we are going from one basis to another using transition matrices. So another example, using linear algebra actually, is if we take 0.22, that's our puppy, and we express 0.22 in different coordinates, depending on the basis. So if we use a standard basis, canonical basis, well, coordinates of 0.22 are still 22. But now if we change a basis, for basis 1103, then the coordinates of the same point, same location, will be 2 and negative 4/3 because we changed the basis. So we changed the language actually. And our transition matrix, which is here, we will see how to compute it, is actually a dictionary. This will help us translate all the words that are expressed in standard basis, so all the coordinates in standard basis, into words or coordinates in the new basis. We will see how to construct this. It's not going to be complicated at all. Another example is if I have another basis for R2, 7, 2 and minus 2, 4, then the coordinates of the same point, 2, 2, will be here in this basis. Different basis, different language, different coordinates, different word. The dictionary is this one, so the transition matrix. It's different obviously because we changed the language. So English-Spanish is not the same in dictionary as English-Japanese. So this matrix is our transition matrix that helps translate every single word from one language to another. The good news about this matrix is it is invertible. So we are going to see how to build it and how to use it to translate words from one language to another or from one basis to another. So now we are going back to the board and start the lecture using numbers instead of a puppy. Everybody can understand the puppy, but apparently when you go for the words, it's a little bit more complicated. So what we want actually here is to answer 3 basic questions. So I'm gonna just write 3 basic questions to understand actually what we want in this section. So the 3 questions we want to answer. So question 1 is how to find coordinates of a given vector in a linear space in a given basis. So every linear space has infinitely many bases. So the question is, if I give you a vector v living in a linear space W, and I ask you find me the coordinates of that vector in a basis B1, how do you do it? So the first thing to do is to answer this question, how to find the coordinates of a vector v in a basis B1 of a linear space W. Okay. Obviously we can have many bases. We start with one and later on the process will be similar to another one if we change bases. So that's one question. And you will see it's very simple. Actually, what you need to do is solve ax equal b, so using our Jordan. Second question is an easier one actually, is given a coordinate or coordinates of a vector in a given basis, the question is, who's the guy? What's the vector? How can I find it? Well, that one is even easier to answer. So the question is, given the coordinates of V in a basis B1, find the vector V. You will see it's not complicated at all, very simple one. And the last question we want to answer is actually to build our dictionary, because all of these are just case by case and solution processes, but we can systematize everything. So in order to build a dictionary from English to Spanish, well, I'm going to build our transition matrix, and then all you need to do is give me a word in English, and this translation tool will produce a word in Spanish automatically. So that will be something fun to do and very easy actually. So the third question is how to build a transition matrix from a basis B1 to a basis B2. So that's the idea. So how do we do this? Again, it's going to be simple. This time, all you need to do is, again, apply Gauss Jordan, but on a special augmented system. So you have your new basis, B2, let's say. In our case, it's going to be B2, then slash, and our old basis, in our case B1, and apply Gauss Jordan. So until when? Well, until you get identity on this side, and on the other side, you will get your transition matrix. So life will be very easy now. So let me try to illustrate how to do all this, one thing at a time. So we will start with the first objective is how to find coordinates of a given vector in a given basis. So if I change basis, coordinates will change. And then we will go to the easiest part, which is given coordinates, find the guy. And then we are going to build actually systematically a transition matrix between two bases. Obviously, if I change bases, I have B1 and B2, I'll get one transition matrix. We know that that transition matrix is invertible, so I can go from B1 to B2 using one transition matrix. The inverse of that transition matrix goes from B2 to B1. So you're going from English to Spanish, and then going from Spanish to English. It's just the inverse. So that's beautiful. What will be interesting is if I give you several bases, so B1, B2, B3, B4, then you will need to build a dictionary or transition matrix between each of these bases. So that's a little bit of work, but the process is always the same. So let's start with the first question. Given the guy, what are his coordinates in a given basis? And I'm going to start with vectors from R4 because I want you to understand that the coordinates in a basis have nothing to do actually with how many entries you have in a vector. So that's something important. And maybe a reminder, how do we know that a vector is in a linear space when we are given a basis? What do you need to do? So this is how you answer it pretty much. So given W subspace of R4 with bases, so plural, so let's take bases B1 and B2. So these are bases for W, and just to make things interesting, so first vector is 1, 2, 3, 4, second vector is 0, 0, 1, 0, so this is one basis for W, and basis B2 for W will be 1, 2, 4, 4, very creative, and 0, 0, 2, 0, again very creative. So W is span of B1, which is the same as span of B2. Okay, cool. So that's my space generated by basis vectors, these and these, so it's the same space. Well, you can verify that this guy is a linear combination of these two guys, this guy also is a linear combination of these two guys, and the other way around. First guy from B1 is linear combination of people in B2, and the second guy in B1 is linear combination of people in B2. That will be your exercise to see if you remember how to do that. So I'm going to take a vector V, so very nice vector for 8, 15, 16, so vector with 4 components. So first question is, okay, it belongs to R4, but does it belong to W? How can you know? Does V belong to W? How could you know that? What's the procedure? Well, we learned that a long time ago. If I want to know if vector belongs to a linear space and I have a basis for a linear space, well, all I need to check is, can I write the vector V as a linear combination of basis vectors? So this is the same as, can we write V as a linear combination of 1, 2, 3, 4 and 0, 0, 1, 0. Well, you could also ask the same question with these two vectors. Why? Because this is another basis for the same space. So actually, it's the same question, and the answer will be the same. If V belongs to W, then it's a linear combination of these two guys, and also it must be a linear combination of these two guys. Now, the good news is the coordinates are just the coefficients that we will get in front of basis vectors. So that's all it is. There is nothing else in it. So we have two basis vectors, so coordinates of V, if V belongs to W, will be A and B, two numbers, and that's all. So how do I find them? So to find the coordinates of V in basis V1, what do I need to do? Well, that's not complicated. I need to solve the equation A, so I'm looking for numbers A and B such that A times the first basis vector plus B times the second basis vector is equal to V, and V is 4, 8, 15, 16. So if I can find these two numbers A and B, then my vector V is a linear combination of the basis vectors, therefore it belongs to W, and at the same time A and B are the coordinates. So we can write like this: coordinates of V in basis B1 are A and B. This is A, not 9. Cool. So How do I do this? Well, we learned that long time ago. What do I need to do? Well, I need to solve the system. What type of system? Ax equal b. Who's A, who's B? Let's write that. By the way, we are going to do the same thing, looking for the coordinates in basis B2. Not a big deal. We know how to do it. So this means I need to solve the matrix system 1, 2, 3, 4, 0, 0, 1, 0, A, B equal to our monster 4, 8, 15, 16. So this is what I need to do. Well, you see that the solution has two components, so that's nice. Which means actually I need to solve augmented system. So I'm doing this once in my life, not twice. This has been done long before, so we know how to do it. This is just a reminder. So I need to solve this. Well, how do you solve it? Well, apply Jordan. Now the good news is, since, well, I know that this guy belongs to the linear space W, I'll have a solution. The good news is the solution is always unique if it exists. Why? Because these two guys are linearly independent, and from the theory, from your column space, row space, you will know actually that you will end up with two rows of zeros, and here you have an identity matrix. If you don't believe, you just do it. So I'll just dump you the solution. So just do the process, it's no big deal. The solution is 4, 3. So the coordinates of vector v in a basis b1 are, so how do we write it? Well, some people write using square brackets, some round brackets, doesn't matter really. So that's what it is. These are the coordinates of vector v in basis b1. So you see, I have only two people in the coordinates. So my set of coordinates contains two guys, even though my vectors are from R4. So this way you understand that the coordinates have nothing to do with actually number of components or entries in your vectors. Okay? So dissociate these two things. That's why we give this example, so you can actually realize that coordinates are just numbers in front of basis vectors. That's all, nothing else. Good? So this is the same vector v we had at the beginning. What I'm going to do now is find the coordinates of the same vector v, so the same puppy, but in another language, another basis, b2. So that will be exactly the same process, but I'm going to use vectors from basis b2. So to find the coordinates, and again, these coordinates will be unique, of v in the basis b2 of w, so it's a basis for linear space. All we need to do is solve. So we had A, B, I'm just going to change letters. So it's going to be C, and what was the first basis vector in B2 was 1, 2, 4, 4, and the other guy I'm going to call it D, and the other vector was 0, 0, 2, 0, and my vector B was 4, 8, 15, 16. So it's the same guy, and I'm just changing basis vectors, and I'm looking for his coordinates in this new basis. What do I do? Well, not big deal. All I need to do is solve the matrix system. I'm going to write it again apparently. Okay. Which is the same as solving augmented system. Okay. So that's it. Need to find a solution. Well, good news. Somebody worked ahead and found the solution. Okay, so the solution for this thing, which means the coordinates. So how do we do? Again, apply Gauss Jordan. It's always Gauss Jordan. Chapter 1. Cool. Okay, so solution is CD, and it's equal to 4n minus 1 over 2. So that means that the coordinates of my vector v, the same bloody vector, in the basis v2 are, so I'm just going to clean this properly. So how we write it? Again, I'm going to write it with square bracket. You can use round bracket, it's up to you, doesn't matter. But you need to indicate the basis. So you see, it's the same vector, so same puppy, same word, but bases are different, so languages are different. Therefore, the words used for the same object will be different. So puppy in English is not the same as puppy in Spanish. Yet it's the same puppy. Hence the coordinates. So our vector was 4, 8, 15, 16. Basis B1 are what I already forgot, 4 and 3, and the coordinates the vector, so the same vector. And the basis B2 are so 4, negative 1 over 2. So it's the same object but two different bases. How do I find coordinates in different bases? Well, I just need to solve the system Ax equal b, where matrix A has my basis vectors in column, and my vector b is actually the vector I'm having at hand, and the solution will be the coordinates. So that's not complicated at all, actually. Very simple. So now one simple question. If I give you a vector 0 from R4, what are the coordinates of vector 0 from R4 in our basis B1? Just for fun. So let's see that. I think many people will be happy to know that this can be solved easily. So question, what are the coordinates of the vector 0 of R4? So the vector 0, 0, 0, 0 in the basis B1. Then you guess the second question is, what are the coordinates of the vector 0 in the basis B2? So how do I find this? What do I need to solve? Well, I need to find A and B such that, so I need to solve simple system. So what are the basis vectors? 0, 0, 1, 0. This is what I need to solve. Well, this is homogeneous system. That's good news. Now, if you learned any theory before, you know when you have two linear independent vectors, because this is the definition of linear independence actually. So if you have two linear independent vectors and you want to find A and B for homogeneous equation, well, the only solution is A equals 0 and B equals 0. Ha ha ha. It's useful to know your theory. Well, if you don't know your theory, you just solve. And then you'll be pleasantly surprised. So the coordinates of vector 0 from R4 in basis B1 are 0, 0. Oops. Ba-bam. Big miracle, huh? Well, guess what? The same coordinates are in B2. Why? Because the vectors that are in the basis of B2 are linearly independent, so the equation, the homogeneous equation will have unique solution anyways. So this is just something that is obvious and trivial, but it's good to remember. Maybe another one. Another obvious one. What are the coordinates of first basis vector from B1 in the basis B1? Obviously, you can answer all these questions the same way you solve the system. So basis B1, we remember, is this guy, so, and this guy. So what are the coordinates of this guy in this basis? So what am I looking for? I'm looking to solve A 1, 2, 3, 4 plus B 0, 0, 1, 0 equal to 1, 2, 3, 4. So that's what I want to solve. I'm looking for A and B. To find them, well, you can do your Gauss-Jordan or be just smart and realize that if you put 1 here, and you put 0 here, you have your solution. Ta-da! So, the coordinates for the first basis vector in the basis B1 are 1, 0. Simple. Now, what are the coordinates of the second basis vector for B1 in basis B1? Well, yes, what is 0, 1? So that is easy, and again, if you don't remember, you just solve the system. It's not a big deal. So that answers our first question, which is, give me a vector, and I'm going to find you coordinates of that vector in a given basis of a linear space. Just one thing, obviously if a given vector that I give you, because I'm evil, that one might or might not belong to the linear space. Well, how do you know? Well, you try to solve the system. If the system doesn't have a solution, well, the guy I gave you doesn't belong to the linear space. So that one cannot have any coordinates in the linear space, obviously. Okay, so that's kind of obvious, but it's good to remind. So that was the first task. Given a basis, given a vector, what are the coordinates of a vector in that basis? Now the second task, which is much easier actually, is I give you a basis and I give you coordinates of a vector in that basis, and I ask you, what's the vector? So that's kind of obvious, it's easy. That's the second part. Given a basis and given the coordinates of a vector v in that basis, find the vector v. Example, again, our base is B1, or let's say the B2. We haven't worked a lot with B2, so let's change a little bit. So B2, where are you? So 1, 2, 4, 4, and the second one was 0, 0, 2, 0. So this is my basis, and I give you coordinates of vector v in basis B2, and those coordinates, well, obviously they have two components. Let's say is -2 and let's say is 5, the other one. So the question is, what's v? So find v. Well, all you need to do is think for 2 seconds, and this says the coordinates of v are -2 and 5 in this basis B1, B2. So what does this mean? You just need to translate and you're good. This means that v is actually a linear combination of these two basis vectors, and the coefficients are -2 and 5. So coefficient in front of the first basis vector is -2. So I copy the basis vector. We change the basis just for fun, so we use the other one. Okay, so this is 0. To be cute, we are on TV. Okay, so all you need to do is compute now. So -2 plus 0 is -2, and -4 plus 0 is -4, and -8 plus 10, that's 2, and then -8 plus 0 is -8. So v is this guy. Now obviously you understand that these are at the same time the coordinates of v in a canonical basis of R4. Well, that's obvious. It's -2 times 1, 0, 0, 0, plus -4 times 0, or you can write it if you wish, just for fun. So what we have as a vector is actually its representation in a canonical basis. So, not a big deal. We don't need to write this ever in life, but just to make sure you know what's going on here. So my vector and its representation in canonical basis, that's the same thing. So you see, this vector v, which is here, its coordinates in bases b2 are -2 and 5. Now I could ask, hey, but what are the coordinates of this guy in bases b1? Well, what do you need to do? Well, you need to solve the system x equal b, as we did before. So we are not going to repeat it for nothing. Let's say I give you coordinates of u in basis b2 again, and this time it is, let's say, 3 and -1 for some reason. So this means that u is equal to 3 times the first vector in the basis. That's why we call it ordered basis. And then -1 times the second vector. And all I need to do is compute. So I have 3, 6, so 12 minus 2 is 10, and then 12. So this is vector u. Its coordinates in basis b2 are 3 and -1. So you see clearly that coordinates have nothing to do with the components of the vector. So that's why we use this example, so you clearly see these things. Don't mix them. So all this was kind of easy because all I had to do in this case is just multiply these coefficients by the basis vectors, add this stuff up, and get my vector. So that's Sherlock Holmes, that's easy. The previous part was given basis, given a vector, find coordinates. That was more elaborate because you need to solve ax equal b. Now, what would be fun is to go from one basis to another basis. What I mean by that is, I give you coordinates of a guy or a vector in basis b1, and I ask you, hey, what are the coordinates of the same vector in basis b2? And then you scratch your head, and you don't know. Well, one way of doing it would be this. I give you the coordinates, you compute the vector, and then you solve the system ax equal b using the other basis. And then obviously I'm evil, and I'm going to ask you for another set of coordinates of another guy, and then you're going to do the same process again, and it's going to take time. And when you're done, I'm going to ask again for another guy, and you're going to do the same process, and at some point you can start hating me. So, in order for you to like me, I'm going to show you how to do all this automatically, quickly, in a smart way. So what we want now, as a third part, is to go from one basis to another. So, given the coordinates in one basis, what are the coordinates of the guy in another basis? Obviously, I need to give you both bases. So one way would be the long way that I just explained, and that's not really smart. And the smart way would be to actually build transition matrix, which is kind of dictionary. Instead of translating one word at a time, you have a tool that automatically translates every word from English to Spanish. Boom. So that would be fun, and that's our transition matrix. So this is n, I hope. So it's always two bases of the same linear space. We have a linear space, we have two bases for the linear space, and we would like to jump from one linear space to another, from coordinates in one basis to coordinates in another basis. So what do we do? The smart way would be to actually build this transition matrix. So what is the transition matrix? It's a square matrix that is invertible on top of that. That's beautiful. And the idea is actually to express basis vectors of B1 in terms of basis vectors of B2, which means you find their coordinates. So how do we do this? Here it is. So again, my basis B1 and B2, just to remind. So 1, 2, 3, 4, and 0, 0, 1, 0. So B2 was 1, 2, 4, 4, and 0, 0, 2, 0. So what I want is having the coordinates of a given vector in basis B1, I want to figure out what are the coordinates of the same vector in basis B2. But I want to do that a lot, and often for a lot of vectors. So I need to be smart a little bit. So the idea is express basis vectors from B1 in terms of coordinates of basis vectors of B2. So I'm going from B1 to B2. So I want to express this vector from B1 as a linear combination of vectors in B2. Then I want to express this vector from B1 as a linear combination of two vectors of B2. So how do I do that? Well, that's not complicated. Again, I need to solve a linear system. So do that. Solve. Now I'm going to be a little bit smarter than the previous time. I'm going to solve this system. So 1, 2, 3, 4. And also solve a system with the same matrix. So it's not really smart what I'm doing now. 0, 0, 1, 0. This is what I'm going to do. Find solution for these. The solution here will be x1, y1, and it's already computed somewhere. It's 1, negative 1 over 2. And solution here will be x2, y2. And somebody computed that also. It's 0, 1 over 2. So what this means is that the coordinates of this basis vector, so given by solution of this system, in basis B2 are 1 and negative 1 over 2. Coordinates of the second basis vector are given as a solution of this system and are 0 and negative 1 over 2. So the transition matrix is actually given by these two columns. And we write it clearly. So transition matrix T from B1 to B2. So it's clear from which coordinates to which we go. And first column is 1, negative 1 over 2. And the second column is 0, 1 over 2. That's it. That's my matrix going from B1 to B2. Which means now I can give you coordinates of any guy in B1, and all you need to do is multiply it by this matrix, and you'll get coordinates in the basis B2. Yeah. So how does that work? Well, let's see. So vector V in basis B1, let's say coordinates are 2 and -2 for some reason. Well, I can find what is vector V, obviously, but all I want now is coordinates of the same vector in basis B2. So coordinates of vector V in basis B2. So what do? I use this transition matrix from B1 to B2, and I'm done. So coordinates of the vector basis B2 are just, so let me write schematically, B1 to B2, that's a matrix, times coordinates of V in B1. So that's schematic. In more concrete terms, I just copy the matrix and multiply by the coordinates of the guy in B1, which are these. And once I'm done, if I know how to compute, I'll get my coordinates in B2. So I have this time, this is 2, plus 0 is 2. Beautiful. So this is -1, is -2. Coordinates in B2. Cute? Then you go, hey man, but they're the same. Isn't that weird? Maybe. Let's try another one. If I give you a vector 2 and 7 in B1, what are its coordinates in B2? So the same transition matrix, all you do is change this, and then you have this, and then you have -1. So -1 plus 7/2. So 5/2. Cool. So those are the coordinates of the same guy in a different basis. So you can do this all day long. And then some smart guy will ask, yeah, but that's good. I'm going from coordinates in basis B1 into coordinates in basis B2. Nice. But what if you're evil to the point that you give me coordinates in basis B2 and then ask me to produce coordinates in basis B1? Should I start the process all over again? Well, that's an option. Or you can compute the inverse of this matrix. That will do the work. So just a note, the transition matrix from basis B2 to basis B1 is just the inverse of this one. So dB2 to B1 is actually the inverse of this guy. So I'm going to write it schematically. You put the brackets. So the inverse. So somebody computed the inverse, and the inverse is B2 to B1. The inverse is cute, is 1102. So this is going from B2 to B1. So if somebody gives you coordinates of a vector in B2, basis B2, to find the coordinates of the same vector in basis B1, all you need to do is multiply by this matrix. Example. Given, or change the name, U, basis B2, let's say it is -3 and 1. Find U in B1. Don't need this anymore. And you see your transition matrix is always square. and is always invertible. Okay, so that's not complicated. So U in B1 is equal to this matrix, so the transition matrix from B2 to B1 times the coordinates of U in B2, which are given. So it's 1, 1, 0, 2 times the coordinates of minus 3, 1. Ta-da. So you have minus 3 plus 0. Then you have minus 3 plus 2 minus 1. So these are the coordinates of the guy in basis B1. If you want to know who's the guy, well, that's not complicated. It's minus 3 times the first basis vector of B1 minus 1 times the second basis vector of B1. But the same guy is actually equal to minus 3 times the first basis vector of B2 plus 1 times the second basis vector of B2. Well, that's not a big deal. It's the same guy, obviously. So that's the way you would proceed in order to find the transition matrix and to go from one set of coordinates to another. It's quite a straightforward procedure. Once you have your transition matrix, you're pretty much set. And one trick, not supposed to tell you, but let's say this will give you some edge. Let's say you need to find transition matrix from basis B1 to B2. Cool. You do it and then you realize that might be a long process. But for some reason, finding transition matrix from B2 to B1 is much easier. Well, guess what? You can do that and then take the inverse. So you get what you're asked for. So that's something you can use if you wish. Just for fun, I'm still wondering who's U. Who's the vector U? We said, well, U is minus 3 times the first vector of B1. Where is B1? No, B2. It's expressed in B2. So B2 was 1, 2, 4, 4. And it's plus 1 times the second vector of B2, which is 0, 0, 2, 0. So we compute this, and we get minus 3, then we get minus 6, then we get minus 12 plus 2, get minus 10, then we get minus 12. That's our guy. We were talking about this guy all the way. So now you wonder probably, is that the same as what we would get if we use these coordinates from B1? Well, let's see. I hope it is, because if it's not, somebody doesn't know what he's doing. 1, 2, 3, 4. So these are the basis vector of B1. Minus 1 times 0, 0, 1, 0. So now your calculator's out. Minus 3, minus 6, minus 9, minus 1 is minus 10. Good news. Minus 12 here. Hey, the same guy. Surprised? No, it's supposed to be the same guy. It's the same puppy, just his name is expressed in 2 different languages. Come on. We knew that. Nothing new, man. So that's how you find the thing. Obviously, the process is a little bit longer if you have vectors with 3 components, but it's not a big deal again. Just one example quickly with 3 components, because by now we know what to do. So I'm going to R3, have 2 bases for R3, and then say find the transition matrix from basis B1 of R3 to basis B2 of R3. And you'll say that's not a big deal, because I know what to do. So R3 span of B2, and I'm going to define B1 and B2. Obviously, these are bases with having vectors with 3 components. So B1 will be a canonical basis. That's cute. And B2 will be some a little bit more elaborated basis, just to have a suffer a bit, sweat from time to time. So 1 minus 1. Cool. So now what I want is to find transition matrices from basis B1 to B2, let's say, or from basis B2 to basis B1, whichever one is easier. And then I find the inverse of the other, or solve again, depends. It's the same thing. So if I want to find the transition matrix from B1 to B2, so find the transition matrix what do we do? Big deal, just solve the system. I need to express every single vector in a basis B1 as a linear combination of basis vectors in B2. How do I do that? Solve Gauss-Jordan, with A being the vectors from B2, and the B, the second right-hand side member, will be this one at the first, then second, then third, and then we solve. So what I need to do actually is to solve a big system. Because it's the same matrix. So simultaneously I'm solving all 3 equations because I'm a little bit smart. I don't want to work for nothing. So once I solve this, I'll get identity on this side, here, and transition matrix on this side. So apply Gauss-Jordan. Until you get identity 3 by 3 here, and transition matrix will be here. Cute. So once you do all this, the transition matrix from B1 to B2 is, well, I computed that, 1 over 2, negative 3 over 2, 1, 0, 1, 0, 1 over 4, 1 over 4, and negative 1 over 2. So this is the transition matrix from basis B1 to basis B2. Nice. So you need to do the process. Well, nothing special, we learned already how to do it. So now question, what's the transition matrix from basis B2 to basis B1? Well, it's obviously the inverse of this one. Yeah, who's going to compute the inverse of that one? Huh? Not me. We need to be a little bit smarter than that. So since we have B1 as canonical basis, this will simplify our life. So B transition matrix from B2 to B1 is equal to inverse of this. That's officially the case. There's nothing new there. And you can compute it and there's nothing wrong. Just long. So it's the inverse of this. Well, I have good news for you. If you compute the inverse, you're going to get this guy here. This is because we are dealing with canonical basis as one of the bases. Life is a little bit simple. So in general, if I give you just 2 random bases of R3, well, you will need to compute the inverse or swap these 2 and then proceed again. So that's the way you do to find transition matrix. So now if I give you coordinates of a guy in basis B1, and I ask you what are the coordinates of the same guy in basis B2, well, not big deal. You multiply the coordinates by this matrix and you get it. So let's say we do just that. Given U in B1 is equal to 202, so in B1, find U in B2. Well, all I need is to multiply these coordinates by the transition matrix from B1 to B2. So the coordinates of the guy U in basis B2, just multiplication. So need to be able to multiply at some point. If not, you have your calculator, hopefully, able to calculate. So 202. So this goes from B1 to B2. And these are the coordinates in B1. And I'm going to get my coordinates in B2. So this 1 plus 0 plus 1/2, so 3/2. So this is minus 3 plus 0 plus 1/2, so 3.5, 7/2. And then you have 2 plus 0 minus 2, no, minus 1 is 1. This is what you get, and those are the coordinates of the same guy in basis, why did I, yeah, it's fine. In basis B2, all good, simple. If you want to know who's the guy, well, you have two ways. Either you multiply these coefficients by the basis vectors of B2, or if you're smart enough to realize that B1 was canonical basis, well, these are the coefficients in front of the canonical vectors, so the vector is actually 202. Something similar, if I give you, so given, let's say, Z in B2, so coordinates, let's say, -1, 2, and 3 in B2, find the coordinates of the same vector, Z, in basis B1. What do? Well, you need transition matrix from basis B2 to basis B1, and then multiply that matrix by these coordinates here, and you're done. Well, lucky for us, we have it here. So coordinates of Z in B1 are given by, so I'm going to schematically write, I'm going from B2 to B1 times the coordinates of the guy in B2. So this will give me what I need. So this is the transition matrix. 1, 2, 1, and 1 times. So this is going from B2 to B1. And I'm taking my coordinates of Z in B2, which are given here. 1 is 1, 2, 3. And do all the complicated computations to get the result, which are the coordinates in basis B1. So let's do it. So -1 plus 2 is +1, and +3/2. So that's 1 plus 3/2 is 5/2 last time. And then this is -1 plus 0 plus 3, so that's +2. And then the last one, -2 plus 2, that's 0, -3. So these are the coordinates of our guy in basis B1. Now, knowing that basis B1 was canonical basis, well, I know also who's Z. Z is just this guy. So that's easy if you know what you're doing. Don't try to remember this by heart. It's totally useless and a waste of time. Don't do it. Understand what you're doing and it's going to be fine. maybe a couple of problems for you just to suffer and have fun eventually. So I'm going to give you simple things in R2. So I'm going to give you 3 bases of R2 and then ask you to find transition matrices from one basis to another. So you'll have like 6 possibilities and then you'll have fun. Obviously all you need is 3 and then compute the inverse. But if you don't know that, it's fine. You compute more. So this is just an exercise for you to go through the process, and once you do that, you're pretty much sure that you know how to find the transition matrix from one basis to another. So, for fun, it's all given bases B1, B2, B3 of R2. So what's B1? Oh, none of them is cute. So this will make you compute. B1, B2, value, 1, 2, 3, whoa, somebody was creative. So this is B3, 1, 3, 2, 3, whoa. Okay, so these are 3 bases of R2. Cool. So what I want now is transition matrix from one basis to another. So find the transition matrices. Transition matrix. So 1. So you go from B1 to B2, and then also you go from B2 to B1. All of these matrices will be 2 by 2 because you have 2 people in the basis. So obviously, once you find this guy is just the inverse, and you know how to compute the inverse of 2 by 2. That's long time done. So going from B1 to B3, and after that you go back, you go from B3, to B1. What do you do? Well, once you compute this, you compute the inverse and you get this guy, no trouble. And the last one, so go from B2 to B3. And once you do that, you can compute the inverse and go from B2, B3 to B2. Excited? So these things you can compute quite easily. The idea is to go through the process. Just apply the process slowly. There's nothing special in there. So that's it about change of basis, coordinates, and how to say puppy in several languages, and how to build a dictionary that will translate every other word, not just puppy, but cat and dog and donkey in different languages. So have fun, solve some problems, and I hope you'll do well in your exams also, as you should, I guess, after this good explanation. Have a good day, bye-bye.
Done?
I guess, but I didn't click on the thing.